Thank you very much. Glad to have everybody back here. It's hard to compete with a good coffee break, but we made it. I'm going to talk about X-ray analysis methods. So sometimes we actually need to use Photoshop to get better data too. Okay, this screen here is very important, I think, if you want to get the basics of the technique. So the methods that I'm going to talk about here, they regard like X-ray in, X-ray out of the sample. So this picture tells you everything of the basics. It tells you like X-rays are photons within this energy and wavelength here. This is actually the interaction volume in a sample. Of course, you can actually get better or worse than that, but typically on a lateral scale, you can go from something like, or on the depth, sorry, you can go from a couple of nanometers to a typically 30, 40, 50 microns, depends on your setup. On the lateral side, some people claim they can do in a lab source, and I think there are some micro diffraction instruments that can go down to 10 microns, but I would say typically 100 microns with good intensity, and depends on the beam, you can go to up to a couple of centimeters. Keep this in mind, because X-ray diffraction and reflectivity are typically large volume techniques, which can be good, can be bad, as we're going to see later. There are lots of effects that comes out from interaction of X-rays with the matter. Some of them actually I'm going to cover. Some of them has been covered already by Rick and will be covered by other people in the SCM talk tomorrow. If I move this now, next slide. Okay, the coherent scattering, which is the basic of the diffraction process, occurs when you have, oops, press the wrong button. Apologize for that. So basically, what happens here is that, let me move back. So, all right, so basically you have an incoming photon. That will generate like an oscillation process in the electron of the atom, and then photon is going to be emitted out there. The key important thing to understand diffraction is that the energy of the outgoing photon here is the same as the incoming one. Now this is the coherent or diffraction scattering here. So now the other situation that you deal is the incoherent scattering when the outgoing energy is smaller. The other process involved I'm not going to touch. People are going to talk about that in the other presentations as well. So, all right, so here is the basic thing. What X-ray deals is with periodic stuff. So this actually is a sequence of atoms in a structure which are ordered. This could be your whole crystal, or it could be just part of a sample, just a grain there. So you need something that's ordered there. So the first thing you do is that we work with imaginary planes. So say, for example, that actually you have these planes that are actually marked according to this here in this picture with the Miller index HKL. Unfortunately, the X-ray diffraction technique does not show a real world image of the material. It goes in this kind of twilight zone, weird kind of world, which is not really the direct world, it's the reciprocal space. The reciprocal space, it can be very intimidating in the beginning, but it's pretty easy once you get your way around. So let's go with me inside that twilight zone world and try to walk around and understand what we see. So basically the representation of this crystal or this grain from what comes from your X-ray instrument, it will be like a Fourier transformation of a set of planes. And in that case, it will correspond to a spot here in the reciprocal space. All these planes here correspond to the spot. That's what your X-ray machine will spit back on your face here, this spot. You say, all that work for this? Okay. Now, let's go on with this concept. If instead of picking up the separation, if I actually change the distance, like pick up closer planes, so I'm going to get a different spot here in the reciprocal space. Remember, 1/day relationship. This goes farther if the planes are closer. Now, if instead of those orientational planes, if I pick tilted planes instead, I'm going to get a spot in reciprocal space, which is a different direction in an angle with the origin. So what is this? It's just an exercise that you just pick things and just draw little cute boxes or circles everywhere there? No. We are actually going to use this in our advantage later down the road, because depending on what information we want to look for, we may actually look for spots that are here or spots that are actually tilted. Okay, so we're going to be walking around there and choosing which one to park. Depends on which information is going to be relevant for us to fish out from that measurement. So this basically, that pretty much correlates the two things there. Direct space, periodicity, and reciprocal space. So if you want to have like a rule of thumb, let's call it like Paris Hilton rule of thumb,
of interpreting features in the reciprocal space. So if you have something in the direct space that is actually long and thin, in the reciprocal space, because of the 1 over d feature, that will show short and elongated sideways. So of course this is simplistic, but it works a lot. If you see like a diffraction feature that's broad, it means that it's coming for something that's pretty small. So large in one space is small in the other one. Now, do not think that if you get like a diffraction from Paris Hilton, you can actually, okay, I can just invert and get the real girl here in the lab with me midnight. I was so alone and bored, so why not do that? Actually, the problem is more complicated because when you go from, try to go from this space to the other one, you are measuring intensity, which is the square of the function. So you lost actually the phase information. So you cannot just actually, this is the phase loss problem in diffraction. You cannot reconstruct the electron density to get the Paris Hilton there right away. There are methods that you can work on that. But sorry, what we learned from this overhead here, do not look for Paris Hilton in the reciprocal space. She will not look very good, so it's better to look in the direct space. All right, so now it actually is the whole grail. If we had to do an adventure movie about actually the X-ray diffraction, the Bragg's law will be like the Da Vinci Code or something very important. What it is. Here I'm going to show you what the Bragg's law here, and also I'm going to show you the corresponding situation in the reciprocal space. I'm showing both the space, our space and the twilight zone kind of space. X-ray beam coming in the sample, angle of incidence, diffracted beam going out there, diffracted angle, the same thing, we have wave vectors there in the reciprocal space. Now, you define a scattering vector, and it turns out that because of the elastic scattering, these two vectors have the same length, then you can derive Bragg's law. Very simple law. If you know, for example, that the angle that the X-ray beam is coming out from the sample, and you have well-defined wavelength, you can calculate the atomic spacing. So as long as you can measure an angle, which anybody can do typically, poor resolution or good, but you can measure an angle, and basically you can find something about a microstructure that you cannot see inside a naked eye. So by just measuring angle, you have microstructure information about the sample. This actually, when you say Bragg's law, there are just two guys here, son and father Bragg, that they did this and they both won the Nobel Prize. Sometimes I feel sorry for the son because you work the whole life. When you get a Nobel Prize, your dad's there with you to share the prize with you. But it could be worse. It could be your mother-in-law there. No, you never know. So, but anyway, that's the basic concept that you actually have to think about in terms of, that's what made the X-ray so popular. The equation is very simple. This guy here, Ewald, created a sphere, and it was called Ewald's sphere. So basically what he says that, okay, this diffraction process in the reciprocal in the direct space, in the reciprocal space can be described as a sphere where the radius is the length of this wave vector, and then when you do a measurement and change these angles, the Ewald sphere is just rolling around, and at any point that you hit like one of these dots, ping, you get lucky. You get actually one intensity there. So this is helpful many times to actually understand the diffraction process. So in a scattering measurement, you get this diffraction count from the sample. You can get basically three scenarios. In these rings here can be continuous rings if your sample is completely polycrystalline. You perhaps have seen this in like some TM exercise, TM results or something like that. If it's a single crystal, instead of these circles, you get dots because the planes are very highly oriented. And in the in-between case is the texture material where you don't have the spots are elongated almost in between these two situations here. Okay, that's enough what I'm going to say. All right. The most basic type of measurement in X-ray diffraction is called 2 theta theta scan, 2 theta omega scan, omega 2 theta scan, theta theta scan. There are many ways people talk about that. But if you want to learn one type of measurement, that's the one you should learn. So what happens here? During this measurement, the angle of incidence and the detector angle change together. So that's why you either do that by rotating the sample or the tube and moving the detector. So actually, when you do that, let's go now to our picture. Direct space, reciprocal space. Now, this is very important for the end of the talk. When you do 2 theta omega scan, the scan that everybody goes in the lab and do, The only thing that you are probing is you are probing the direction that is perpendicular to the lattice planes. If you have planes that are tilted, you are not seeing them. You don't see, you cannot pick them up. So 2 theta omega scan just picks the information that goes, see what is varying across these planes here. Therefore, it's a very useful scan to check these spacing separations, variations that you have. So that is a signature of strain variation, composition change. All right? Now, what's the next thing? The other situation is the rocking curve, where only the angle of incidence is changed. Let's start the TV there and see what happens. Only the sample is changing, the angle of incidence here. So basically, you are not going perpendicular to the planes. You go across the planes. So basically, your D space is basically constant. So as you move around, if you have irregularities across these planes, like defects, it's very sensitive. So 2 theta omega scan that you do is good to pick up composition, strain change. For more defect information, rocking curve omega scan. Keep in mind those 2 things. So what I just said there. So now in a basic X-ray measurement, again, let's go back to our 2 theta omega scan. As you're scanning, the sample is changing the detector. You are actually go from low to high angles, for example, and you stand any point that you see like a peak there is because you have hit a set in the crystal where you have a periodicity. Now, this picture is also very important to understand artifacts. Notice this, that because I just said that 2 theta omega scans only probe planes that are perpendicular to the scattering vector, and this is parallel to the surface, I'm only measuring, detecting the orange ones. Look at the planes there. The tilted ones, I'm not seeing them. Now, if I want to see them, I have to make sure my sample is random enough so that these guys here that I'm missing here, they will be rotated down in the sample and show up there. All right? So that's the limit of the technique. You just pick up some of them. Another thing that's important, look, as I go to deeper and deeper angle, look at this, the size, the lateral size is reducing, and you are going deep as well. Keep in mind that if your sample is not constant or homogeneous in the whole volume, you may be picking up different information as you go to different angles. Those are potential artifacts, that information that you get, for example, at high angles may be slightly different from the low angles, especially if we're going to compare intensity. So from the X-ray technique, basically we actually look peak positions, we identify the materials. Width will actually be information about size and strain, and area of the peak about the orientation. The diffuse scattering, which is like the noise near the peaks here, will be used for point defects, and we also even use the background. Actually, good job, I forgot to set up the timer. Okay, and the amorphous background here is actually used for, the background of the data is used to identify amorphous. We actually use everything in the data. We don't throw anything away. We're kind of efficient and green technique. We don't waste anything there because we don't have too much sometimes. Now, let's go to different applications. So I'm going to start with the case where you have unknown materials, as you don't know the structure that you have there, or you have a material that could be a film or a bulk, which everything is typically random. Okay? Grains are randomly oriented. So the basic technique, the basic configuration that we have is what they call the Bragg-Brentano focusing configuration, where the X-ray beam comes from the source. It's actually diverged, hits the sample, and is guided back and focused back in the detector. So this is a technique, this is a configuration that's very nice because it's very well understood, the peak shape, the mathematics behind is very well understood, and actually but it has some things that are key. It's very sensitive to the sample height. If you put your sample at the wrong height in the instrument, or if you don't have the sample well located in the height, you get the peaks completely in different position. And good luck proving to your boss that the material that you have is actually that material, because he'll not agree, oh, that position of iron, that's not where iron should be, it's something else. So that's a very important thing. That's a very common artifact in this kind of technique. Let's go to the beach now. Oof, I got tired. This is actually, I'm going to walk you through data analysis in one sample, which I was like a couple of years last year. I was in the beach, and then I decided to catch there a piece of rock. And then I decided, oh, what's going to look at this? The first thing we did was actually to grind it. Why did I grind it? Well, I want to make that this is, since I didn't know what it was there, and inside, I had some idea. I ground it basically so to make it in fine power to make it random. Okay? And then to make things even more fun, means complicate, I added some amorphous there, which I know the amount was there. So then took that in the X-ray machine. So this is one X-ray machine that we show in the tour. The most important thing here is not this rotation that's going on there. It's the tube rotation and the detector rotation. This is the 2 theta omega scan. You got the data that's already acquired there. You can see you have diffraction peaks, but you have a hump here that typically suggests you that you have amorphous. I knew because I put the amorphous contents there. But that's the signature of that. What can we get with this data? Let me show you step by step. First, here I run the sample before I mess it up with amorphous. So you can see the hump there is actually due to the amorphous amount, the disordered amount that I added. So here in the blue you have the sample without the amorphous and you don't see that hump. So then the next thing we did peak fit. Why do we do peak fit? Why can't I just go there and mark with my eye? Peak fit is a much more rigorous way to go there and identify where the peaks are, what's the area of the peak, the width of the peak, all the properties there. So basically we take the data, we put some peak shape function. We know basically what the shape should be. Is it Gaussian? Is it Lorentzian? Is it pseudo-void? What is that function? Typically depends on the configuration. Most of the time, pseudo-void does a good job, but we also have to enter the instrument resolution as well there. What's the typical width that comes from that? When we do all that, we fit the peak through a computer software. Basically, we get a list of peaks marked there. So everything is identified. You can do more calculations from that. So now what we did here is that we look at the area. Okay, we look at the area. We look at the area of the peaks. The area that is above the curve is the crystallinity, the amount of crystalline phases, 80% to 20%. That's basically what I put there when I actually prepared the sample. So the background here under the curve will be corresponding to the amount of amorphous. Of course, we subtract the background from the sample holder. Okay, what the heck's in the sample? I got the sample, I measured, I found where the peaks are. Now let's run these peaks against the database. So the database of material, there are many databases around. So most famous one is the PDF4 database. So what you are going to compare is peak position and relative height of the peaks against the database. When you do that, in the old times, maybe when early times, just joking, but maybe very old time, people used to do this manually. Nowadays, with 500,000 cards in the database, try to do that. You know, maybe you can take, if your kid is very messy and making mess, then you can do like a job for the kid to keep you in peace and do like a search match manually there. But nowadays you do actually, or if you have a naughty student, basically you actually do that with the computer. So now when you do that, basically the computer gives you a few hits. Okay, let's consider the first one, which is a mineral called calcite. Actually, it goes and found that some of the peaks are matching exactly with that. So next step, we go and do a second search match round, focusing the peaks that we have left behind. So when you do that, the software actually points that dolomite, which is another mineral. So part of this structure was one mineral, the other part was the second mineral. You could really be in a nightmare situation that you have 4, 5, 10 phases. People in the cement industry, they have like lots of phases to work on that particular analysis. In this case, to make it simple, just 2 phases there. So what next? So basically we identified what is in that sample there. What's the present, surprisingly simple. Next thing we're going to do, okay, how much? Next, you found what it is there, but how much of each part? So how can I find out? The easiest way to get quantification is just to get the area of the peaks. The area of the peaks is proportional to the amount of material you have there, right? So the ratio of the area of the peaks will give a kind of ratio, but you have to keep in mind that that's not the whole story. Some materials, let's put like this, are easy to give X-rays. So even if they have a small amount, they show lots of X-ray coming out there. Look, I'm here. So they see a lot of peaks. Some of other, no, you have them a lot there, but they are shy and just show a few peaks. So you get a misleading information. I have seen many times people just taking the area of the peaks and say, oh, I have 20% and 50% of the, wrong. You have to enter a factor, that's the IRR, reference intensity ratio. You can ratio them to each other or to Corundo. That's typically a factor that you can either calculate yourself, measure, or you can get from the database. So basically here to understand, I talk too much, but what you should carry from this transparency, area of the peaks can be used, but you have to ratio each area by a calibration number, that's the IRR, then you get an approximate number. Now the problem here that you just deal with the peaks. You don't include actually the amorphous phase. We get like about 1 to 4. That's the ratio between the two phases there. If you want to be more rigorous, you have to do something that this fellow that's looking up there on you, see there? He developed, Rietveld. Many people do that. Nowadays, it's very established the software. What this does is that for each data point in the curve, including the background, you are going to minimize the difference between the measured and a theoretical curve. So then you do that through a software to minimize that, and then you get like a structure, a refinement that will come from the software. Basically, what you do, you get your data, you have to know a little bit about the structure. And you crank the software, and you refine everything, background, sample displacement, peak shape, all the things you can imagine there, you refine, and then you get a lot of information. So when you run this sample through the Rietveld refinement, few important things we got. The percentage of each phase, and you can see that 1 to 4 ratio is similar to the IRR method, the amorphous, and you get the grain size as well. It's a very powerful method, and you get more information about the details of the structure, the two phases that are present. But you have to be careful. I have seen many people coming in the lab, very excited, wagging their tails there. I want to do Rietveld. I want to do Rietveld. I said, why you want to do Rietveld? My boss told me. My wife told me yesterday I should do Rietveld. You have to know when to do, because you may be opening a can of worms. You have heard of the thing that, how do I put in a way that's not going to be censored in the video? Crap in, crap out. Right? So if you have bad data acquired with very poor statistics, the software will fit and you crank out wrong numbers that are not physically possible. You want to do Rietveld, you have to be able to invest the time to acquire good data. But it's something that it pays off in the long run, because you get very accurate information. Oh, this one. This can be a source of fight in the lab sometimes. Grain size analysis. Many people come almost in tears. I don't know what's happening. I measure my X-ray data here and I get a grain size, and I go in the SEM, it's different. My boss is giving me a hard time. My wife doesn't talk to me. My dog doesn't even bark to me at home. You have to help me with that. What is going on? Take it easy. You have to understand what are the assumptions on the different techniques. What you are actually measuring. Are you measuring exactly the same thing? The direction is the same? Then they calm down a little bit. It's almost like doing X-ray. It's almost like a therapeutic. You have to be like a little bit a psychologist, shrimp, and you have to talk to people, calm down. But let's see what's going on here. How can we measure grain size by XRD? You got your peak, right? You got your peak. You know the position. You know the width of the peak, how fat, you know how slim the peak is. And remember, you are measuring just in one direction. You can use these parameters to estimate the crystallite size. This is the size in the crystal that is ordered and giving that peak for you. So this is the shear equation. It's very simple. You know this guy is here, a constant lambda. You know the position and the width. Boom. You calculate the grain size. So basically, let me give you examples here. Before I move to the example, something that's very important to remember. First, it's a very simplistic approach. You are assuming that everything in the width of the peak is size effect. There's much more. There is defects. There is the instrumental function. There's a lot of things there you don't even want to hear about. But anyway, as long as you know that your approximate is fine. Also, it's a very directional measurement. I have seen many people, when you see, for example, if you have a sample that's a very long column, if they measure the grain size sideways, it's going to be small. They come in the X-ray and measure the height of that tower. It's going to be long. So they cry, so we are measuring different directions. That's why. So then they get happy. They kiss me, give me a tip maybe, and then go and so on. Life is better now. But you have to understand that. Now, it's very important when you do, okay, this is a few examples. Nanoparticles, see 2 nanometers, very broad peaks. Remember, big thing here in the reciprocal space, very small in the direct space. You hear this is a very large grain, very sharp peak. That's a type of extreme case you can measure by just look at the width of the peak. You actually have to be very careful about the function that you use to fit your peak. You have to enter the instrument function, because inside that peak you have an intrinsic width from the optics. I can see I'm in trouble with the time there. We have intrinsic, so you have to correct for that. Let me give you like a horror case. a horror case for you to see how things can go really bad if you're not careful. Let's say, for example, that you have an instrument with this peak width. You measure some peaks, 0.3 or a little bit of 2 degrees peaks. That's the width of the peaks you measure, okay? You have the positions, everything. Then let's say that one student in the same group takes the data and he actually calculates using a Lorentzian function. The other one does a Gaussian. Look what is happening here. So if the peak is actually very broad, the instrument correction doesn't matter too much because the peak is big. It's like you have an elephant and you have like a little ant there, doesn't care. Now, imagine if you have something that's already small and you have a significant part to correct. So it's very important. So if they use different methods and one of them is not, you can get a 50% error, difference between the data. So bear in mind, you have to have your instrument function very well determined. Also, be aware on publications. People tend to claim things that they are not careful. They just, who is this? Poltergeist or something? Okay. Anyway, I was talking about bad thing about people. Okay, another thing that I should move pretty quick now is if you want to introduce in the width of the peaks, if you want to add the strain information, there is another method that you can add size plus strain. You assume this equation here for the strain contribution, and then basically you get this Williamson-Hall method. People work with metal materials, they love that. I see a few of them sitting there and nodding their head. So you have to be careful because it does not work all the time. You need a couple of peaks, but if actually what you do, you plot this in a certain way, and then basically what you get is that from this simple curve, you can get like from the intercept, the size and the strain. When it works, it's beautiful. In many cases, don't work. Oh, but my boss allowed me to do like Williamson-Hall, and someone from your group, actually, not you, but from your group, it doesn't work, I don't know what to do. Well, the system is more complicated than this. There are dislocations that you are not accounting for, point defects. This is just a simplistic thing, right? But it's a good first step, actually. Many people publish a lot with that. Now, one example that is common is the thin film and bulk. Let's say when the things become more ordered, more like organized, the grains are not totally random. Then the configuration that's typically preferred is what they call parallel beam configuration. You see the beam is made parallel through the optics when it goes the sample and get out there. The advantage of this is that this is more tolerant to sample height displacement. You can have a sample that's a bit off and should still be fine. It's very good also for glancing angle, which I'm going to talk about, and it's excellent for samples that are not regular shape. If you have something that's rounded, like an egg or something like a piece of a brick, or like I got a few months ago, like a piece of a piston from Caterpillar that had a weld. You know, the welding part was a mess there, a bubble and everything looking ugly. They asked me to measure there. So the only thing you can do with this configuration, if you do Bragg-Brentano, it's going to be a mess. You don't see peaks. Peaks are very weak. Parallel plate, parallel beam is excellent for that. Thin films, irregular sample, glancing angle, bulk pieces, for example, is great configuration for you to use. One example, a thin film. Tantalum nitride film grow on MgO substrate, deposed by sputtering. So, okay, they go happy there. They just do the 2 theta omega scan. Run there, simple. They were happy. Only thing they saw, a substrate peak and a film peak. The difference is here's the different samples, depends on the energy of the sputter. But that's all they see. So what they conclude, okay, we know that you are probing the direction perpendicular to the surface. It means the 001, the film, is the parallel to the substrate. And then many people here do one mistake. They go out in the hallway celebrating, oh, we did that, this means the film is perfect. It's epitaxial. Because I have the orientation is matching exactly there. Well, remember the 2 theta omega scan I told you? You are just probing this direction. You are just seeing that in one direction is well aligned. This orientation with the substrate, how about implant? That can be completely different. In that case, you must do a different measurement. You have to look at a tilted plane, which we did here. Then we did a certain type of scan, and we found out that for the tilted planes, they have very sharp peaks aligned with the substrate, which is good news. That means in the tilted planes being aligned means the film is actually a epitaxial film that grows like cube on cube. So this cube grows exactly on top of that the story is very beautiful and happy. But in many cases, that's not the case. Sometimes the cube will grow actually rotated relative to the other part. Now, one thing that I know many people use, especially I think Greg, for example, has lots of students using that in his projects in the UIC, is the glancing angle. So what happens if you are really in bad shape and your film is either too thin or you don't have enough intensity? Then you have to really use some dirty tricks for that thing. So what you do? Well, what you do in this case is that you keep your angle of incidence very short, very small, and you come very glancing on the sample, like an airplane just going to land there. So when you do that, and you just rotate the detector, so when you do that, you'll be probing not only the direction that's perpendicular, but you'll probe other directions as well. The basics of this process is because of this curve here. This is the penetration depth as a function of the angle of incidence, and you can see that it changes a lot with the angle of incidence. So what it does is that the penetration depth is actually very small at small angles. So what you do, you come at a very low angle here, and basically you are going to focus all your analysis probe in the film area or in the surface area, rather than going deep. I'm just going to skip through an example here. A polysilicon film on a silicon substrate was done. The red one is the regular 2θ omega scan. Look at the size of the substrate peak. This is huge. This is like your brother-in-law coming to the party. He takes over, he eats all the food, he changes the TV, the remote. He doesn't do, so he takes over the whole thing. Now, too much, right? So when you do the glancing angle, you go so shallow that you don't see your brother-in-law, the substrate. You don't have a chance for him to show up. So then the peaks from the surface, from this film here, they show higher. Look at the blue ones. Even one that was hidden there can appear there now. You can measure. So you get a much better quantification there. You have a lot of examples that by using glancing angle, not only you can emphasize the intensity from the film, if it's thin, but you can also probe different depths. You can actually play with that. Now, texture. We talk about grains being random or being oriented. Texture deals with this. Okay, you talk about the grains being random, but how many grains are actually oriented or not? Hopefully, right now, if you guys were grains, you will be texture looking at me. But there are a few random there, but that's fine. But basically, in the coffee break, everybody will be looking at different direction. Of course, unless Paris Hilton walks by there, then everybody will be looking, but everybody will be randomly oriented, looking there, machine. So this is basically the texture, the orientation of the grains. So we want to find out ways to actually how to figure out that particular process. I'm not going to go too much over this table here. It's actually unhealthy after lunch to look at these things. So basically what you do, you can go from very simple things to complex, using ratio of the peaks, and going to like very complex pole figure measurements where you tilt the sample in all the possible directions and measure where the grains are. So perhaps I'm going to just focus a little bit on the pole plot. Have a grain with an orientation. Here you have the vector. When you project that either in this mode or that mode, you get a spot there in the pole plot. That tells you exactly the orientation of the particular grains there that you have used. So I don't think I'm going to go over this. I'm running out of time. Basically what people do, they measure these pole plots. Basically what it says here, for all the orientations here, when you have strong intensity, that's where the grains are oriented. In this particular sample, what was a copper foil that was rolled, these particular angles, that's where most of the grains are oriented. Now, this tells you only the orientation of this particular phase. If you want to find out what is the orientation of all the phases, you do a bunch of these guys here. You do a calculation called ODF, Orientation Distribution Function. A lot of people from the civil, mechanical, and engineering, they do that. Then you get this ODF plots. As a function of angles in the sample, you get where actually the grains are more oriented there. I'm not going to go in detail on that, just like a hint of what can be done there. One thing that happens a lot, especially like in the end of the year or when you're at the end of your paychecks, is stress. So basically, X-ray can actually provide a very simple method to measure residual stress. What we are good to do in X-ray is to measure variation on the D spacing. If you actually know elastic properties and you know you can use Hooke's law, you can actually figure out the stress tensor in the material. It's very simple. Remember your old 2θ omega scan that we talk about? The same thing you do, but you do it tilted. You tilt the sample back and forth, And if you have a stress, the peak is going to show at different locations. Then you get if you are lucky, you get like a simple equation here, where based on this, the slope, you can get the stress. What I want you to take from this slide is this. Can X-ray measure residual stress? Yes. It can quantify it? Yes. If it can tell if it's positive, negative, compressive, tensile, yes, it can do that, but you need peaks. If the material is amorphous, you can't do that. You have to use other methods. Let's move a bit quicker here. This is high resolution now. In some situations, you definitely want to have high resolution. I see some guys there smiling and look at the picture. All right, so when do you need high resolution? To look at Pamela Anderson? No, actually to look at single crystal or to look in case of have epitaxial high quality films on a substrate. Basically, this situation is this. The actual position of the peaks, they are so close to each other, like twins, that in an old machine, in an old instrument, you don't separate them. You need high resolution. High resolution is defined in this way. The capability of actually separating very close by peaks. How the hell high resolution is done? I have heard about this, but nobody ever told me this. This is your lucky day. I'm here to tell you, to break you the news. So it's very simple. You have an angle of incidence. You see, if you have an uncertainty in defining this angle of incidence or in the diffracted angle, so this uncertainty here will generate a confusion in where the evil sphere is located when you're doing the measurement. So instead of actually being like just a tiny spot, you have a confusion here, an area of uncertainty. You see that the more you make this certainty of the angles that you get the beam in and out, the tighter is that spot that you measure. So all the high resolution instruments, they actually work in this way that they make the beam very narrow angularly, either coming in from towards the sample or out of the sample. That's the key, using multi-reflection crystals. So when the beam comes out there, it comes behaving very nice, very parallel. So we are talking about a difference of like 0.003 of a degree versus like a tenth of a degree. So quick examples, and I think it's Barry around here still. Yeah, Barry has worked with this a lot in the past. I think multi-layer, superlattice, quantum dots, things that are very close to each other you can do. One quick example here, a classical indium gallium arsenide on gallium arsenide, for example. You measure that, look at this peak width. Your grandmother's X-ray diffractometer will not be able to separate this because it's poor resolution. So look at this, it's very small peak width. Not only you can see the peaks from the film in the substrate, but these fringes here can give you the thickness of the material through a simulation, and you can actually get, for example, the composition. Now I'm going to move to something that's called reciprocal lattice mapping. It's still high resolution, but what is this? So far, we have been so lame that you are just seeing things in basically one dimension. We just see like an intensity there. Let's open the box, let's open our mind and see things in 2 or 3 dimensions, right? It will actually show us a lot of new features. You remember that when I show initially these dots of the reciprocal space? We're going to see them, how they look in real life. We're going to look at these dots now. The peaks that you see in the X-ray data, they are just projection and integration of these dots. We're going to see and catch those dots right now and see how they look like. So ready for that? Let's go. That's what reciprocal lattice map does. I'll skip this so you can read. For example, a silicon germanium material, very popular in microelectronics. One of this study here was investigating how the thing behaves when you heat it up, when you anneal it, see if it's stable or not. When you grow this, what you get there, you get your 2 theta omega scan, peak here, there, beautiful, get thickness, very well. It looks like the film grows very nice in the substrate. As you start annealing, the whole thing collapses. This beautiful peak becomes broad, fat, low there, like, very unspeakable. So basically, what is going on there? That's all you get from the scan. Let's look this in 2-dimensional. Introduce your reciprocal space map. These are actually the dots that I pointed for you there. Remember, we go to some directions, depends on what, these are the dots. I'm sorry to report, but they don't look really nice, depends on what, see, they look blood. So this is real life, my friend. Sorry to break the news. Things like, you see, for example, pictures that are nice, like when you are dating online, they send you a picture that looks very beautiful, but when you meet, That's what actually you see in real life. So it's something like that. But let's understand what went through here. So what is this? What you're showing here, Mauro? What the hell is this thing here? Well, these are the scans. Actually, imagine if you take like an helicopter, it could fly on top of this and see this from above. So you could be able to see how this peak spreads out like a mountain in multiple directions. That's what you are seeing here. So that guy is here, very sharp, but elongated. That guy is here. The one that is really fat there, you see, that's the guy. That's the substrate there. But here, most important, you can see where they are exactly, and you can see how they distort. To make the story short, you see initially as they grow, they are very well aligned, meaning that they are very low. There is a good match of the lattice constant. As you start annealing, there is some diffuse scattering that's generated there. Basically, defects start being formed. As you go to higher and higher temperature, these peaks not only they go off alignment, indicating like a different lattice constant, but you have the diffuse scattering. And you can do like it's party time. You can calculate things from there, defects, density, and so on. You get a lot of information. You have to agree with me. You will get much more information from this actual kind of result than just for the simple scan. You can actually get direct lattice constant measurement in multiple directions as well. And of course, we extract kinetics of that. We could interpret the data and see what is going on with this dislocation. In a nutshell, you start annealing, dislocations and defects goes like crazy. They go very much like they start propagating very quick. Up to some point, it becomes very crowded. Like people go inside a bus, you cannot get more. So the rate of dislocation, they start pinning each other. No, you cannot come here anymore because they were already here. So that's what they do. So the rate of defect formation becomes actually, and you can get all the kinetics at very high resolution there. I have one more example that you can read by yourself in the presentation. This is available online. Actually, I just got the information that they posted today. Peak shape of the reciprocal space actually would be able to tell you all these things. So by looking at the peak and see where is elongated to, in which direction it's going that particular elongation, you can tell if it's like a defect formation or if it's like a composition change. Maybe the material is just changing composition. You can get all that. I don't have time to go over these details here, but it's there. You can take a look on these, before you go to sleep, bathroom, you can just sit and read all this thing here. The last thing I want to talk about is reflectivity. Reflectivity is a completely different thing. This is more for extremely thin materials, and the only thing that we're looking for is nothing to do with crystallinity. We don't care if the sample is crystalline, order, or if it's a royal mess. We don't care. It became very famous because actually you can measure density, thickness, porosity, and roughness as well. How is it done? Again, 2 theta omega scan. But it's done with a trick at extremely low angles. You see, the angle of incidence is very small, the detector is very low. And when you run there, what is happening here, this kind of reflectivity plot. So here's very low. I'm going to describe this to you through an example. I'm going to skip that. These are examples you can have. You can measure amorphous. I'm going to show you this case. Silicon substrate, a very thick oxide, and a polymer. Just a couple of nanometers. Run reflectivity. What the heck is going on here? Okay, with the beam very small, the angle of incidence, very small, you just actually bounce off the surface. After some point, you hit the critical angle, you actually start going the sample, so the amount of beam coming out, reflected out, is small. This is your reflectivity curve. Now, depending on the slope of this curve, you can tell about the roughness. The faster this thing drops, rougher is the material. Also, you can get this kind of envelopes or fringes that will tell you about the thickness, and that's why the technique became popular. In this case, you see that you get 2 envelopes, one with very little fringes, and the one with a big hump there. So they can be, this is related to the oxide thickness, and this big lump here is the polymer thickness. So when you do this thing plus a simulation, we can actually get information about the densities, the thickness, and the roughness, not only in the surface, like your EFM friend can do for you, but also at the interface. So it's a very powerful, and look at the thickness of this polymer, 2 nanometers. Now, good luck going out there and finding on a regular basis some technique that can measure 2 nanometers for you. All right? Let's compare X-ray with other techniques. How does X-ray do? Is it good, bad? Let's see, I'm going to be very impartial here. Very neutral, I'm not going to push towards X-ray, so compared with the other ones. So basically, all right, so I'm not going to have you reading this. Just quick, very little sample preparation. In other techniques, you have almost to bleed to death to prepare the samples. TM, for example. X-ray, very minimal preparation. That's applause there. No problem with vacuum. So you can put like, even dirt and disgusting samples in our machine. You can do that. Composition, we can go to like a couple of percent. Below that is hard. XRF can do ppm. Of course, other techniques will do better than that, can do better, but they typically involve destroying your sample sometimes, making holes, and torturing your sample. So now, lattice cost, that's where we are the king of the hill. That's why we're the boss of the thing. This part, we are good. X-ray can measure lattice constants at very low angles, very small values within 10 to the minus 5 or better. So this is where we are. TEM, for example, can do 10 to the minus 3. Other techniques, they just don't do it. How about thin film thickness? X-ray can do like 2 to 500. The main problem here is that the sample has to be with flat. If it's too rough, we can't measure. Other techniques also, they actually can do measurement for you. There's a lot of competing techniques I made. Some of them will require destroying the sample, have good contrast. Ellipsometry is a very good alternative technique that you can use as well. So basically, crystalline size, oh Jesus. So we have to remember that X-ray measures volume and it's just in a particular direction. Other techniques, they do a number and they can be completely different directions. Texture and stress, remember you are measuring over large volume. Other techniques like EBSD go very small. You have to compare to keep that in mind. How can you measure through the depth? You can use glancing angle to get like a depth information in terms of the grain size and the stress variation. Interface roughness, major competing technique is actually AFM, scanning probe techniques. They tend to be limited just to the surface roughness. They do a good job there. We can actually simulate and get the budded interface as well. Defects, that's where we really suck. X-rays. You need to put lots of modeling, and you know this guy, the salesman that tries to talk to you to sell, to buy that old car. We have to do that kind of thing, Oh, the model here, and he gets another model. That's the part where X-ray needs improvement. There's lots of models for different things, but how you can get actually defect quantification from X-ray data. It's basically looking at the width of the peak and assuming some functions, the tail of the peak, diffuse scattering. It's not a clear-cut thing like in the TM. You just see the points there, the beetles run inside the sample or some bugs, whatever. We don't see that. So that's the part that you need lots of modeling. That we could do better. The cost. X-ray instruments are not so expensive. You can buy a tabletop one to put in your dinner table for $60K. You can have some very good instrument for $200K, and you can have a pretty much of a Rolls Royce at $400K. Compare that to other techniques involving vacuum. We'll talk about $1 million instrument. So it's pretty much a very competing technique. Now, we compare them. Let's see who is going to be the winner. You think I'm going to choose the winner is? You have to agree with me. X-rays, right? X-rays. X-ray. Okay, I just lost a few microscopist friends here today, but the summary of the technique is this. It's a non-destructive. Do we still have time for that video thing? Yeah, right? Yeah. Okay, you can read this by yourself. It's a quantitative, non-destructive, fingerprinting. Basically, you can actually identify what's in the material. Basically, you can actually choose the levels of complexity. You can just get your 2 theta omega scan and then go to the bar and brag the whole night about that. Or you can actually just do something more complicated. So you can choose the level of complexity that you are going to go with this technique. Of course, the negative side, as I said, we are pretty much operating in a large volume. So basically, with X-ray, it's difficult to lie. With the TM, you can find a corner in the sample. That's the only corner that's nice. You publish the X-ray, my friend. It's large volume. It tells you the whole thing. That's why if the sample is not good, it will basically give a good average there. There are ways to go more specific. Microdiffraction is one way. There is a way to look at nanocrystals like pair distribution function. A lot of new ways there. Okay, I'm going to conclude now. If you have seen, I apologize if you have seen this video last year, but you have learned about X-ray today. Let's show now a video quiz. This is a video from CSI where they actually have one of the characters going and using an X-ray machine to solve a crime. So you're going to look at that, and I'm going to ask questions afterward. You will see what you think or not. The vendor of this instrument has nothing to do with this movie. They told me they just was asked to put the machine there, and the Hollywood guys did the rest. So now you saw that. What you guys think the Hollywood guys got right or wrong about this? Let me walk you through. First, okay, piece of sample there. Okay, that piece of metal can be analyzed by X-ray. Rough like that, parallel beam optics will be a good thing to do. No, don't need to cut, just stick the thing there. What am I supposed to talk about this guy? Okay, yeah. In the chemical identification, in the percentage that you come out from that, you could use that in principle to try to narrow down where it came from. So if that is if that's like that composition is a bit weird and unique, you can track down from which shop the guy or which vendor came that thing. They can track down which car had that and so on. So that guy had a point there. He got right. Now, another thing, they are actually using a real X-ray machine. The guy is wearing lab coat. He's wearing gloves. Another thing, if you have used the expert machines, you know that he's using the dial gauge to get the sample height correct. Otherwise, the sample height is going to be wrong. Peaks will go a bit different location. They cannot solve the crime because they cannot narrow down what material is there. So point for him. Good job. Now, that's where the thing starts weird. Dude, you are pushing the wrong button. The machine was already on, and that button, if you have done the tour, you'll see, that will turn off the machine, not start it. Data analysis solve the crime. Good. Next thing, that's weird. An X-ray beam you can see, and it actually eroding the sample, you know? See, it's eroding the sample throughout there. All right, but this is not the worst. The worst thing is this. 3 things. First, money. They show money there. Find money in the X-ray lab. Good luck. Typical XRD user? Tim, maybe you can send them a proposal to be a user here. This never happened in the X-ray lab. What I'm doing wrong? Guys, thank you very much for the attention, and thanks for the sponsor.
Do we have any questions for Mauro? Nobody has any questions? I guess that whole thing about mother-in-laws and what we can do after lunch.
Distract everybody, you know?
Yeah, there's nothing left.
Yeah. Well, one thing maybe I can add is, in terms of the facilities I showed here, one thing that we'll be able to add heavily in the future next year is the capability to go to more localized places. You know, have a lateral spatial resolution much narrower through focusing optics. So where you can actually narrow down exactly the area, if down to 100 microns or more. I know this is very important for some projects. Like, for example, some people like to take a look at a metal structure and find out how the texture is changing to point by point. So with a large beam, you can't do that because it averages everywhere. So with this kind of optics, and also, since this makes the beam small, you need on the other side the detector improvement. Nowadays, you have not only point detectors, you have linear detectors and area detectors. It's a whole can of worms that I did not want to show here today because it would be too much. But that's where the technology is going. X-ray is not standing still. It's going towards faster measurement. Have a question?
If you have a sample that you don't want to pulverize,
Yes, very good question. Some samples you cannot actually make it in powder. Examples. For example, let's say Well, we have had that. Some samples that came from Krannert Museum, she came with the little pellets there. She said, you cannot destroy it. We didn't know what it was. You cannot destroy it. No sweat. So what we did, we put in the X-ray machine. We did the measurement. Right? We got the peaks, but then we had to be careful in the data analysis because when we do the search matching, we know that the peak positions will be correct, but the relative intensity might not be correct because the sample is not random. So we have to allow, and the software let us do that, do a search match, but laxing a little bit, that's an excellent question. We see that problem all the time. And not only this, when people have texture samples, that they cannot be random. They go run through a database, they get confused. But you have to allow for this fact that actually samples can be, not only this, some materials are explosive. You can't actually pulverize them. You cannot make them like a small piece. They can blow in your face, for example. There's no method to do. You have to run them. The key is, I would say a parallel plate, maybe it will be a parallel beam configuration will be good to avoid any of this waving on the sample. And be very careful with the data analysis, allowing for texture orientation. It's a very, very important problem. Thank you. Okay. Oh, question there? Okay, yes, please. Yeah.
When people do surface excellence diffraction, they need to
They do what?
surface excellence diffraction.
Yes.
When they correct data, they need to consider a factor one-yard profile.
Do what?
One-yard profile. Because, but I don't know if it's very detailed. But when they do extra random reflection, they don't consider this correction.
Correction for? I didn't understand the word. Well, there are, well, I don't, we can discuss that, but basically I did not have the time to go in detail, but you actually have to, when you quantify, especially at low angle of incidence, there is some kind of corrections for absorption, refractive index that actually some software, you can actually use manual, you have to correct for that to get thickness out and numbers out there, yes. That has to be taken into account. But come back, we can discuss exactly what that is. I just touch a little bit the top, you know, there is of detail that can go there. Yes, who else?
So you showed a couple of examples of doing diffraction of nanoparticles.
Yes.
Exactly the smallest sample size can be used.
Well, yeah, it depends on this. When people come there, and if they have a choice of choosing, I'll say, you want to do, you are the person who actually likes to get the things done easily and comfortable, or you like to suffer? Basically, it's like if you have like a very small contents, you have to scan for a very long time so that you have the condition for the peaks to be well above the background. Sometimes it's not people like to suffer. They don't have enough material. They have, for example, nanoparticles in droplets. They just put there. There is no remedy. They have to scan and make the measurement for like a couple of hours, sometimes even overnight. But the good news is, on the contrary to actually microscopy, you don't need to sit there for 4 hours. You start, go to a party, come back, as long as you are not so wasted, and then you get the data out. That's it, it's done. Now, I would say the more you can do, the better, because you would like to have, depends on your instrument, you would like to have your sample being illuminated by the whole beam. If you can do that, your chance of getting better data quicker are actually higher. Better detectors will help you too. Faster detectors will do a good job. Did I answer your question?
Well, I was just looking for like a relative fast.
It depends on the instrument you use. In our instruments, for example, I would say let's say if you have like a powder, comfortably, if you have a half cubic centimeter, it will be perfect. We can fill up our cavity holder, fantastic. Now, other cases I have seen people come with nanoparticles in solutions. They just take a glass slide and they drop it there and let it dry a little bit. I say, okay, spread as much as you can. A few drops, and the more you do, the better it is. So it depends on also depends on the material. If you have a material, for example, like iron oxide, it may not scatter very well, especially iron, so you need to collect longer. The best thing of this is I gave you some rule of thumb, but the best day is like if you come to me at some point, we know exactly the material you have, which instrument is going to be used. I can give exact specifics there.
If you have any other questions, why don't we refer those to Mauro separately after we get back downstairs?
Okay.
But let's let's thank Mauro one more time.
Thank you.